Welcome to this explainer. Today, we're jumping right into a realm of material science that honestly sounds like pure science fiction, but is rapidly becoming an engineering reality. We're talking about the fascinating world of organic superconductors and their applied uses. For decades, the idea of conducting electricity with absolutely zero resistance was strictly confined to rigid, freezing cold inorganic metals. But what actually happens when you bring organic chemistry, the building blocks of life and everyday plastics, into the quantum realm?
Okay, so let's kick things off with a massive what-if that completely flips our understanding of ordinary materials. Look around you right now. Plastics are insulators, right? They block electricity. But imagine for just a second, what if the flexible, lightweight polymer backbone of a plastic wire could be engineered to conduct an electrical current with perfectly zero resistance? No heat loss, absolute perfect efficiency. It's a concept that really challenges our fundamental, everyday understanding of how materials are supposed to behave.
Here's our roadmap for today. We'll be looking at 1. The superconducting plastic dream, 2. The physics of Cooper pairs, 3. Carbon-based superconductor families, 4. The temperature challenge, and 5. Next-gen applied uses. All right, diving right into Section 1, the superconducting plastic dream.
Back in '64, a physicist named W.A. Little completely shattered the prevailing scientific dogma of the time. Up until then, superconductivity was exclusively the domain of rigid inorganic metals that had to be cooled by liquid helium down to near absolute zero. But Little proposed a really radical alternative. He theorized a long, conducting organic polymer spine, essentially, with highly polarizable dye molecules attached to it as side chains. He believed this specific molecular architecture could unlock superconductivity at incredibly high temperatures, maybe even room temperature. It was this bold, beautiful idea that instantly ignited a feverish global quest.
Moving on to Section 2, the physics of Cooper pairs. So, to really get this, the crucial point is that superconductivity fundamentally relies on electrons, which normally repel each other, right? Somehow finding a way to pair up. We call these Cooper pairs. When they bind together, they condense into this single, massive quantum state. Instead of bouncing off the atomic lattice and creating friction and heat like normal, they just glide perfectly through the material. It's kind of like two perfectly synchronized dancers moving through a crowded room without bumping into a single person. But the million-dollar question is, how do you get two negatively charged electrons to stick together in the first place?
Well, this brilliantly illustrates the contrast between the traditional view and Little's vision. In standard metals, which are described by the famous BCS theory, the glue that holds the pair together is a phonon. That's a slow, low-energy vibration of the crystal lattice. Little, however, proposed an excitonic alternative. He suggested using the incredibly fast, high-energy electronic excitations within those organic dye sidechains to bind the electrons together. Because electrons are practically weightless compared to atomic nuclei, the energy scale of these excitons is vastly higher than phonons. And, in the math of superconductivity, a higher energy glue theoretically means you get a much higher transition temperature.
Which brings us to Section 3, carbon-based superconductor families.
Looking at how this all unfolded historically, superconductivity itself was discovered way back in 1911, and scientists finally nailed down a theory for it in 1957. Then, boom, Little drops his bold proposal in 1964. But it actually wasn't until 1980 that a team led by Denis Jerome finally discovered the very first true organic superconductor. Now, it was a quasi-one-dimensional organic salt, and sure, it only worked at around 1 Kelvin and under intense pressure, but it proved the core concept: carbon-based materials absolutely can superconduct.
And since that 1980 breakthrough, scientists have synthesized an entire zoo of highly ordered carbon-based molecular crystals. We've got quasi-1D Betchgard salts, the layered quasi-2D Bet TTF salts, and 3D alkali-doped fullerenes, which are basically doped buckyballs. We've even seen it in simple hydrocarbons like piscine. What's absolutely wild here is that these aren't just conventional superconductors, they're playgrounds for unconventional superconductivity, where strong electron-electron correlations and Mott physics are often providing the pairing glue rather than just simple lattice vibrations.
All right, Section 4, the temperature challenge.
Now, despite decades of really intense research, 38 Kelvin is the absolute highest confirmed transition temperature achieved so far in these organic materials. Specifically, that's in cesium-doped fullerenes. Just to put that into perspective for a second, 38 Kelvin is about minus 390 degrees Fahrenheit. That is literally colder than the surface of Pluto. So clearly we're still quite far from Little's ultimate dream of a room temperature organic superconductor. And reaching even that 38 Kelvin still requires extreme pressure.
Our source material hits on a pretty harsh reality with this quote. The fragility of the organic molecules and the crystal structures may also inherently limit TC. We're currently battling what physicists call the TC problem. Basically, organic structures are relatively soft, they're easily disrupted. Finding a way to push these temperatures higher so we can avoid the need for incredibly expensive, extreme liquid helium cooling remains one of the absolute greatest hurdles in condensed matter physics today.
And finally, Section 5, Next-Gen Applied Uses.
So, here's the clever workaround. If we can't make a pure organic polymer superconducted high temperatures just yet, why not mix the best of both worlds? By blending inorganic superconducting nanoparticles, like niobium nitride for example, into an organic polymer paste, researchers have created superconducting organic polymers, or SOPs. You get the incredible quantum functionality of the metal particles, completely combined with the flexibility, processability, and the adhesion of a plastic. Think about it. You can literally screen print a superconducting circuit. And look at how this translates directly to the real world. We can actually embed these hybrid nanoparticle and SOP materials right into structural components. We're taking the very foundation of our infrastructure, our cement, our architectural coatings, our building blocks, and we are injecting them with these highly responsive, conductive networks. We are literally talking about transforming passive infrastructure into intelligent systems. Imagine self-sensing concrete that can detect its own microcracks before a bridge ever has a chance to fail. Or smart architectural coatings that are self-cleaning and antibacterial. We can build entire energy-efficient facades with embedded energy storage. And over in the high-tech sector, these printable, flexible superconducting films are absolutely perfect for the complex, low-temperature packaging required for quantum computing arrays, where brittle, traditional superconductors tend to just crack under the thermal stress. What's amazing is that specific chemical combinations are driving this whole revolution to meet very precise engineering needs. For instance, mixing carbon nanotubes with the polymer PDOSS gives you self-sensing concrete. Silica mixed with polyaniline creates crack-sensing smart coatings. And cobalt oxide paired with PDOSS allows us to embed massive energy storage directly into walls. It's highly customized material science solving huge, macro-scale problems right before our eyes. And honestly, here is where it gets truly futuristic. The next frontier isn't just about raw performance anymore. It's about sustainability. Researchers are now looking at using biotechnology, specifically microbial fermentation, to eco-produce the conjugated monomers needed for these very polymers. Instead of relying on and constantly refining petrochemicals, we could use engineered microbes to literally grow the building blocks of these advanced electronic and superconducting plastics. We are talking about merging green chemistry directly with quantum electronics. Which leaves us with a really profound question to ponder as we wrap up. How might the convergence of biotechnology and superconductivity entirely rewrite the future of sustainable energy? Just imagine a future where the materials powering our lossless energy grids, our quantum computers, and our smart self-healing cities aren't mined from the Earth, but are grown in bioreactors. The Excitonic Dream might have started as a quest for a magical plastic wire, but is rapidly evolving into a blueprint for an incredibly sustainable, technologically astonishing future. Thanks for joining me on this explainer, and keep questioning what's possible.